Hello children, once again welcome back to Physics with Sanoop, Healing Medical Aspirations. Now let's discuss PYQ of NEET from the chapter Rotational Motion. Okay, we will discuss all the questions that appeared in past NEET papers and also AIPMT before that. Okay. And here is the first question given below are two statements. One is labeled assertion and reason like that. See, first statement is when a firecracker explodes in mid-air, okay, fragments fly in such a way that the center of mass moves in the same path which the firecracker would have followed if it had not exploded. That's a true statement. Explosion of cracker means after explosion each fragment will follow its own parabolic path, but the center of mass of all the fragments will continue to be in the original parabolic path. Okay, so the first statement is true and explosion of cracker is only due to the internal forces. Okay, that is the reason. That is also true and reason is the correct explanation of assertion. Okay, so A is both A and R are correct and R is the correct explanation of A. Right? Now let's see what we have next. See, two objects of masses 10 kg and 20 kg respectively are connected to the two ends of a rigid rod of length 10 meter with the negligible mass. The distance of the center of mass of the system from the 10 kg mass is. See, the easiest way to find this is if you want to find the distance of the center of mass from 10 kg, you have to choose the position of the 10 kg as the origin. Okay. Okay, then the x-coordinate of the center of mass means that will be the distance from the origin or it will be the distance from 10 kg. Okay, now we have this is the formula for the position of the center of mass or x-coordinate of the center of mass if the two objects are supposed to be on the x-coordinates. Okay, and see, we have chosen the position of 10 kg as the origin because we have to find the distance of the center of mass from 10 kg. Okay, now see, m1 that is 10 kg but x1 equal to 0 and m2 that is 20 kg and x2 is equal to the length of the rod and it is 10 meter. Okay, and in the denominator we will have 10 plus 20 that is equal to 30. So 200 divided by 30 or 20 by 3 meter. Okay, 20 by 3 meter. Now we have another question. Three masses are placed on the x-axis, 300 gram at origin, 500 gram at x equal to 40 centimeter and 400 gram at x equal to 70 centimeter. The distance of the center of mass from the origin is. See, we have the formula for a two-particle system. The same thing can be extended for any system with any number of particles. Okay, now let us write the formula for a three-particle system. Okay, and now we have 300 gram at the origin and its x-coordinate is 0, then 500 gram at 40 centimeter, 400 gram at 70 centimeter. Okay, and in the denominator m1 plus m2 plus m3, so that will be 1200, and in the numerator, see, this is we can take that 100 or 1000 we can take outside. Okay, so in the first this term will be 0 and this term will be 5 into 4 20 and here it will be 4 into 7 that is 28. 20 plus 28 will be 48. Okay, 48 divided by 12 that is equal to 4000 divided by 100 that will be 10. Okay, so 40 centimeter. 40 centimeter means this is the correct option. Okay. And next question, let's see, a solid sphere of radius capital R is placed on a smooth horizontal surface, means there will not be any frictional force. A horizontal force capital F is applied at a height h from the lowest point for the maximum acceleration of the center of mass. Okay, now see, here the acceleration F equal to mass into acceleration where A is the acceleration of the center of mass. Okay, and this A will be equal to F by m, means force divided by mass. So the acceleration of the center of mass in this case is independent of the heights. Okay, so the acceleration will be same whatever h may be. So this is the correct option. Okay. Now let's see what we have next. The center of mass of a system of particles does not depend upon mass of the particles. It will depend. Forces acting on the particles, it will not depend. Okay. Center of mass will not depend on the forces acting on the particles. Then position of the particles, definitely. Center of mass will depend on the position of the particle. Relative distances between the particles. Okay, so only the second option will be the correct. Okay, carbon monoxide molecule, the carbon and the oxygen atoms are separated by a distance 1.12 into 10 raised to minus 10 meter. The distance of the center of mass from the carbon. Okay, then you have to choose the carbon, position of the carbon as the origin. Okay, now see, this is the formula for the x coordinate of the center of mass of a two particle system. Okay, and the position of the carbon atom we have chosen as the origin, or x equal to 0. Then the position coordinate of the oxygen atom will be x equal to 1.12 angstroms. Okay, so this is the position coordinate of the center of mass, 12 into 0 plus 16 into 1.12 divided by 12 plus 16. So here we have 12 divided by 24 into 1.12, and this we can write 3 by 7 into 1.12. Okay, 3 by 7 into 1.12. Okay, now 7 into 16 is 112. 7 into 16 is 112. So 1.12 divided by 7 will be 0.16. Okay, 0.16 into 3, that is 0.48 angstroms. 0.48 angstroms. 0.48 into 10 raised to minus 10 meter. Okay, now let's see the next question. The angular acceleration of a body moving along the circumference of a circle is, angular acceleration is an axial vector. So it will be along the axis. Along the radius, that is wrong. Along the radius towards the center, that's also wrong. Along the tangent, that's also wrong. Along the axis of rotation. Okay, so this one, right? Next, two particles A and B are moving in uniform circular motion in concentric circles of radii RA and RB with the speed VA and VB respectively. Their time period of rotation is the same. The ratio of the angular speed of A to that of B. Okay, they are moving with the same time period. See, we have angular velocity omega equal to 2 pi by t, or angular velocity 2 pi being a constant, angular velocity depends only on the time period. See, time period is same for both the bodies, so they will have the same angular velocity, or angular velocities angular speeds will be in the ratio 1:1. Now let's see the next question. A particle starting from rest moves in a circle of radius r. It attains a velocity v0 meter per second after the nth round. After the nth round means after completing a distance 2 pi r into n. In each round it covers a distance 2 pi r. So after nth round means distance travelled will be 2 pi r into n. Okay. And see, its angular acceleration will be, angular acceleration, see, angular acceleration alpha is given by, see, at, that is the tangential acceleration, equal to alpha into r, where alpha is the angular acceleration. Now first let us find the tangential acceleration. Tangential acceleration means the acceleration is everywhere on the circular path, it is along the tangent. So the velocity and acceleration are along the same direction at any instance. Okay, so the instantaneous displacement will be along the direction of instantaneous velocity. And acceleration, instantaneous displacement and acceleration are always along the same direction. So you can apply v square equal to u square plus 2as. Let me repeat, you can apply v square equal to u square plus 2as because acceleration and displacement are always along the same direction, that is along the tangents. Okay, now see, this is the velocity after the nth round v0 square. See, the particle starts from rest, so u0, u square 0, then 2, this a is the tangential acceleration. Okay, this a is the tangential acceleration, a with the suffix t. Okay, and the displacement after nth round will be 2 pi r into n. okay, along the tangents. Okay, so 2 pi r into n, and we will get a with the suffix t equal to v0 square divided by 4 pi n r. Okay, that is at, and alpha will be at by r. This is at by r. So if we divide this by r, we will get the angular acceleration. That is v0 square divided by 4 pi n r square. v0 square divided by 4 pi n r square. Okay, now let's see what we have next. A wheel has angular acceleration of 3 radians per second square and an initial angular velocity of 2 radians per second. In a time of 2 seconds, it has rotated through an angle. Okay, see, initial angular velocity is given, angular acceleration is given, time is also given. We have to find the angular displacement theta. Okay, so you have to use the equation which is similar to S equal to ut plus half at square. Okay, and here we will have theta equal to omega 0 t plus half alpha t square. Omega 0 is given as t 2 and t equal to 2 seconds again. Okay, half alpha is 3 and t square means 2 square. Okay, here we have a 2 and this 2 can be cancelled. Then here we have 3 into 2, that is 6, 2 into 2, that is 4. 6 plus 4, that is equal to 10 radian. Okay, 10 radian, this one. Okay, now let's see what we have next. A wheel of radius 1 meter rolls forward half a revolution on a horizontal ground. The magnitude of the displacement of the point of the wheel initially in contact with the ground. See, initially this point is in contact with the ground. After half a revolution, this will be on the top, and it must have covered a horizontal displacement of pi r. So this is pi r and this is 2r diameter. Now see, this distance we have to find out. Okay, this one, right? Now consider this right triangle. Consider this right triangle. Okay, this is pi r and this is 2r. So by Pythagoras theorem, see, this will be under root pi r square plus 2r square. Okay, what is common? The r, that we can take outside. Okay, and see, if we take the common factor outside, r outside, then under root pi square plus 2 square. Okay, that is pi square plus 4, and r is given as 1 meter. R is, radius is 1 meter. Okay, so it will be pi square plus 4 under root pi square plus 4. Okay, now let's see what we have next. What is the linear velocity if angular velocity is given and the position vector is also given in component form? So linear velocity v equal to omega cross r. Omega cross r. Okay, so we have to form this determinant and evaluate it. Okay, suppose we are evaluating this determinant along the first row. Okay, take this element I cap. Okay, now I cap, we have to eliminate the row and the column containing that particular element. So it will be minus 4 into 6, that is minus 24, and minus 6 into 1, that is minus 6. Minus 24 minus minus 6. Okay, minus 24 plus minus plus 6. So it will be minus 18 I cap. Okay, if see this we have to take positive, and next element j we have to take negative. Okay, now see, in this case we will have to eliminate the column and the row containing that particular element j. Okay, so 3 into 6, that is 18, 5 into 1, that is 5, 18 minus 5, that is 13. Okay, and there will be minus j, minus 13j we have. Okay, now next that is k, we have to eliminate the row and the column containing that particular elements. Okay, k cap, what remains? 3 into minus 6, that is minus 18, 5 into minus 4, that is minus 20. So minus 18 minus minus 20, minus 18 plus 20. Okay, that is plus 2k. So minus 18 I cap minus 13 j cap plus 2k cap, that is the linear velocity in vector form or component form, let us say. Okay, now children, we have another question here. The angular speed of an engine wheel making 90 revolutions per minute. See, in 60 seconds it makes 90 revolutions. So in 1 second it will make 90 by 60 means 3 by 2. Okay, so we will get 2 pi into nu. Nu means it is the frequency. Frequency we have 3 by 2. Okay, so it will be 3 pi radians per second. Okay, 3 pi radians per second. Now let's see the next question. A uniform rod of length 200 centimeter and mass 500 gram is balanced on a wedge at 40 centimeter mark. See, the rod is uniform and it is of 200 centimeter length. So as the rod is uniform, its center of mass or center of gravity will be at its geometrical center, means at 100 centimeter mark. So the weight of the rod, that is 500 gram or 0.5 kilogram, will be acting through 100 centimeter mark. So that I have shown here. 0.5. So the force is 0.5 kilogram weights. 0.5 kilogram weights. And at 20 centimeter mark, we have a 2 kilogram mass. And at 160 centimeter mark, we have another unknown mass of m kilogram. Okay, the rod remains horizontal. Means the clockwise turning effect is balanced by the counterclockwise turning effects. Okay, if it is supported or balanced on the wedge, okay, this weight, this 2 kilogram weight, see, if we fix the rod at this point and a force is applied like this, it will tend to turn the rod like this, counterclockwise. And counterclockwise turning effect is force into lever arm or perpendicular distance. Here the force is 2 kilogram weights and perpendicular distance will be 20 centimeter to 40 centimeter means 20 centimeter. Okay, difference. So 2 kilogram weight into 20. That is the counterclockwise turning effect. That must be balanced by the clockwise turning effect. A clockwise turning effect, we have got two components. One is this 0.5 kilogram weight and this separation will be 40 centimeter to 100 centimeter means 60 centimeter. So 0.5 kilogram weight into 60. And the next is this m kilogram weight and it is from 40 centimeter to 160 centimeter means 120 centimeter. So it will be m into 120. And here 0.5 into 60 means 30, 2 into 20 means 40. 40 minus 30 will be 10. And m we will get 1 over 12. Okay, 1 by 12 kilogram. Now let's see what we have next. Find the torque about the origin when a force of 3J Newton acts on a particle whose position vector is 2k meter. Okay, now we have tau equal to r cross f, position vector is 2k cap and f is 3j cap. Okay, j cross k is I and cross product is anti-commutative. If j cross k I, then k cross j will be minus I. Okay, so we will get 2 into 3, that is minus 6 I cap Newton meter. Okay, a solid cylinder of mass 2 kilogram and radius 4 centimeter is rotating about its axis at the center at a rate of 3 rpm. Okay, the torque required to stop after 2 pi revolutions is, see, in each revolution it will turn through 2 pi and there are 2 pi revolutions. So the total angular displacement will be 2 pi times 2 pi or 4 pi square. So theta will be 4 pi square. Okay, yeah. See, this is, suppose finally the angular velocity is omega and final kinetic energy will be half I omega square. Initially it is at rest, so initial kinetic energy is 0. Final kinetic energy minus initial kinetic energy is the change in kinetic energy and it is equal to work done. In rotational mechanics, work done equals torque into angular displacement. Okay, see, we have to find out the torque. See, here it is a solid cylinder. Moment of inertia is mr square by 2 half moment of inertia mr square by 2 and omega is 2 pi into frequency, and frequency it is given as 3 rpm, 3 revolutions per minute. So frequency will be 3 divided by 60, 3 by 60. So 2 pi and frequency is 3 by 60. So that is omega whole square, means omega square, half I omega square. that is the change in kinetic energy, equals work done means torque into angular displacement. I have told you, the angle described in each revolution is 2 pi and such 2 pi revolutions. So 2 pi times 2 pi. Okay, so n is or angular displacement is 2 pi times 2 pi tau. Okay, now see, we have to find this torque. Okay, this is 4 pi square. Okay, here we have 4 pi square and here we have 4 pi square, that can be cancelled, and this 2 and this 2 can be cancelled. Okay, and see, here we have a 20 square means it is 400. Okay, and on the and in the numerator we have 16 into 10 raised to minus 4. Okay, 16 into 10 raised minus 4. Here 400 into 2, that is 800. Okay, now see this, when this 100 is taken to the numerator, it will be 10 raised to minus 2. So it is 10 raised to minus 6. Then 16 by 8, that will be 2. So 2 into 10 raised to minus 6 Newton meter. 2 into 10 raised to minus 6 Newton meter. Okay. Now let's see what we have next. The moment of the force F equal to 4I cap plus 5J cap minus 6K cap at okay, that is the 2 0 minus 3 about the points. Okay, 2 minus 2 minus 2. So this is the location of the object, position of the object, and this is the reference point, or this point we have to choose as the origin, or we have to find the torque about this point, 2 minus 2 minus 2. Okay, now see, this one is the reference point and this is the point where the body or particle is located. Okay, so the position vector will be see this OP, and in component form that OP will be, see, 2 minus 2, that is 0 I cap. Then 0 minus minus 2, that is 2j cap, minus 3 minus minus 2, that is minus k cap. So it will be 2j cap minus k cap, that is the position vector. And force is given in component form, 4I cap plus 5j cap minus 6k cap, and R cross F will give you the torque. Okay, now that is R cross F. Yeah, we have the determinant here. Okay, I, J and K. Okay, these are the components of R and these are the components of F. Okay, let us expand this along the first row. Okay, so when you take that I cap, you will have to eliminate the row and column containing I cap. Okay, so 2 into minus 6, that is minus 12. 5 into minus 1, that is minus 5. Minus 12 minus minus 5. So it will be minus 7 I cap. That is the first component, minus 7 I cap. Okay, now let us take the next element, that is J. Okay, see, this we have to choose positive and this should be negative. Okay, so minus J, we have to eliminate the row and the column containing that element. Okay, so 0 into minus 6, that is 0. Then 4 into minus 1, that is minus 4. 0 minus minus 4, that will be plus 4 into minus j, so minus 4j cap. Okay, and finally we have to take the element k. Then we will have to eliminate the row and column containing that element. Okay, see this row and column containing that element. Then 0 into 5, that is 0. Minus 4 into 2, that is 8. 0 minus 8, that will be minus 8 into k cap, so it is minus 8 k cap. So minus 7 I cap, minus 4 j cap, minus 8 k cap, everything negative. Okay, so this is the correct option. Now let's see what we have next. A rope is wound around a hollow cylinder of mass 3 kg and radius 40 cm. So its moment of inertia will be same as that of a ring, and it is mr square. Mass is 3 kg and radius 0.4, so it will be 0.48 moment of inertia. Okay, what is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? Okay, so torque tau equal to force into perpendicular distance. Here it is equal to the radius. Force is 30 Newton and radius is 0.4, so it will be 12 Newton meter. We have to find the angular acceleration. that is torque by moment of inertia. So 12 divided by 0.48 and it is equal to 25 radians per second square. Here it is the angular acceleration, 25 radians per second square. Okay. Now two rotating bodies A and B of masses m and 2m with moments of inertia Ia and Ib. Okay. Ia and Ib, and Ib is greater than Ia, have equal kinetic energy of rotation. La and Lb be their angular momenta respectively. Then see, the kinetic energy is given by L square by 2m. See, that is equivalent to the relation in linear mechanics, say K equal to P square divided by 2m. Okay, P is the linear momentum, K is the translational kinetic energy, half mv square, and m is the mass. See, this is kinetic energy, this is linear momentum, and 2m, m is the mass. Okay, similar relation in rotational motion. This is rotational kinetic energy, half I omega square. That is equal to, this is angular momentum, L. Okay, instead of linear momentum. And 2I is the moment of inertia that corresponds to mass in linear mechanics. Okay, now here we have two bodies with the same, if La and Lb be their angular momenta, two bodies with the same kinetic energy, which one will have greater angular momentum? Okay, now see, angular momentum is under root 2EI. We have two bodies and both the bodies are with the same kinetic energy. So the angular momentum will be proportional to square root of the moment of inertia. Moment of inertia is more for the second body B. So angular momentum will be more for the second body B. Okay, so LB greater than LA. LB greater than LA. Okay, now see, a particle is attached to a string. Okay, now see, that particle is revolving in a circle over a horizontal surface. Okay, now suppose there is a hole at the center of the circle. Okay, and that string is passing through that hole. Okay, so the string is coming like this. Okay, string is coming like this. When that string is being pulled gradually, then the radius of the circular path in which the this body is rotating, that will get reduced, or the radius will go on decreasing. So the force acting on the particle will be along the string or along the radius, so it will not produce any torque. So angular momentum will remain conserved. Okay, angular momentum will remain conserved. Now let us see, a mass m is moving in a circle on a smooth horizontal plane with velocity v0 and at a radius r0 initially. Okay, the mass is attached to a string which passes through a smooth hole in the plane as shown. Okay, now the tension in the string is increased gradually and finally m moves in a circle of radius r0 by 2. Okay, radius is reduced. Okay, the final value of kinetic energy is, I have told you, angular momentum will be conserved in this case. Now see, initially moment of inertia I equal to mr square. And final moment of inertia I dash equal to m into radius is reduced to half. So it will be r by 2 whole square. So I by I dash equal to 4. Now kinetic energy, see, we have the relation in linear mechanics, kinetic energy, this is equal to P square divided by 2m. P is the linear momentum and m is the mass. Corresponding quantities in rotational motion. See, corresponding to this translational kinetic energy, we will have rotational kinetic energy E. Corresponding to linear momentum, we will have angular momentum L divided by 2. Then corresponding to mass, we will have the moment of inertia. So L square divided by 2I. Here we have two cases. See, in the first case, the particle is revolving in a circle of radius r. And in the second case, it revolves in a circle of radius r by 2. So the change is only in the case of moment of inertia. There is no change in angular momentum. Okay, so the kinetic energy is, see, in both the cases, this L square by 2 is the same. First case, second case, L square by 2 is same. So E proportional to 1 by I, where I is the moment of inertia. So E dash by E will be I by I dash, and that we have 4. So E dash will be 4 times the original kinetic energy. Okay, so E dash will be half mv square v0 square, that is E, and E dash will be 4 times of this. So this into 4. So it will be 2mv0 square. 2mv0 square. That is a beautiful question. Okay. Now let's see the next question. A rod of weight W is supported by two parallel knife edges A and B and is in equilibrium in a horizontal position. The knives are at a distance D from each other. The center of mass of the rod is at a distance X from A. Okay, the normal reaction on A. Okay, now suppose the force exerted by the knife edges A and B on the rod are F1 and F2. Okay, we have to find F1. Then it is easy to take, easy when you take the moment about this point B. Let us find the turning effect of the remaining two forces about this point. So if we fix the rod at this point or hinge at this point, okay, this W, this weight will provide a counterclockwise turning effect, and this F1 will provide a clockwise turning effect. If this rod is hinged at this point, okay, or if we fix a screw at this point, and if we apply a force like this, it will turn the rod like this, and this force will turn in the opposite direction. As it is, as it is in equilibrium, it remains horizontal, so the turning effect in these two directions must balance each other. Okay, now this F1 into what is the distance, that is D, and W into what would be the distance, it will be D minus X. So F1 will be W into D minus X divided by D. W into D minus X divided by D. Okay. Now let's see what's the next question. An automobile moves on a road with a speed of 54 km per hour. The radius of its wheel is 0.45 meter and the moment of inertia of the wheel about its axis of rotation is 3 kg meter square. If the vehicle is brought to rest in 15 seconds, okay, the magnitude of average torque transmitted by its brakes to the wheel is. Okay, now let us see V, the velocity, initial velocity 54 km per hour and it is equivalent to 15 meter per second. How do you convert kilometer per hour to meter per second? Multiply by 5 by 18. Okay, so it is 15 meter per second. And angular velocity is actually V by R. Okay, now see alpha is the angular acceleration. Now an automobile moves on a road with a speed of 54 km per hour. The radius of its wheel is 0.45 meter, okay, and the moment of inertia 3 kg meter square. If the vehicle is brought to rest, finally it is brought to rest. So angular velocity final, that is 0. Okay, initial it is omega. Okay, and omega by time will give you the angular acceleration because the final angular velocity is 0. Okay, so initial angular velocity we have V by R, that stands for omega. Omega by T will give you alpha. Okay, V I have written 15, R is 0.45 and time is 15 seconds. Okay, so it will be 1 by 0.45 alpha, or we can write 100 by 45. Okay, or you can write 20 by 9. 20 by 9, that is alpha. And tau equal to I alpha. What is I? It is given that 3 kg meter square. So 3 and alpha is 20 by 9. So the total will be 20 by 3. 20 by 3, that is 6.66 Newton meter, or that is the torque, kilogram meter square second raised to minus 2. Okay, so this one, right? Now let's see the next question. Point masses M1 and M2 are placed at the opposite ends of a rigid rod of length capital L and negligible mass. The rod is to be set rotating about an axis perpendicular to it. The position of point capital P on this rod through which the axis should pass, so that the work required to set the rod rotating with angular velocity omega 0 is minimum. See, work done equal to change in kinetic energy. Initially the rod is at rest, so its kinetic energy is 0. And finally, suppose the kinetic energy is half I omega 0 square, in which half is fixed and omega 0 square is also fixed. So the change in kinetic energy, that is equal to work done, equal to half I omega 0 square, in which half and omega 0 square are fixed. So work done will be minimum when moment of inertia is minimum. See, moment of inertia is minimum if the axis passes through the center of mass. Okay, now suppose the rod is rotating or the system is rotating about this axis. So that axis should be passing through the center of mass, or this point is the center of mass. Let us take that center of mass as the origin. So the x coordinate of the center of mass will be 0. This is the formula to find the center of mass, that must be equal to 0. And this mass m1, that is towards left, so its x coordinate will be negative, that I have put minus x. And this is to the right and its x coordinate is L minus x, so m2 L minus x divided by m1 plus m2, that is the x coordinate of the center of mass. See, we have chosen the origin at the center of mass. So the x coordinate of the center of mass will be 0. Okay, so we will get m1 x equal to m2 into L minus x. So here we will get x by L minus x equal to m2 by m1. Okay, now let us apply the componendo dividendo rule. I have explained many times before, componendo dividendo rule. Now see this numerator here it is x, that I have kept as it is, no change. And in the denominator, see what I am going to do now. I am going to add this numerator and denominator, and that sum I will put in the denominator. So L minus x plus x will be L, that I have put in the denominator. On the right side also you have to keep the numerator as it is. Then sum of these two must be in the denominator, means m1 plus m2. Okay, see, componendo dividendo rule is actually if a by b equals m divided by n, okay, then you can write a minus b divided by a plus b, this is equal to m minus n divided by m plus n. Okay, or you can write, see, a divided by a minus b, this is equal to m divided by m minus n, or b by a minus b equals, say, n by m minus n. Whatever you do on the left, same thing should be done on the right side also. Okay, so we have got this x by L equals m2 by m1 plus m2, and x will be m2L divided by m1 plus m2. X will be m2L divided by m1 plus m2, means this is the answer. Okay, now let's see what we have next. Force is given in component form. Position vector is also given in component form. The value of alpha, because see, in the expression for force, its x component is alpha. Okay, that's a variable, it's not given, that we have, it's an unknown rather than variable, it is an unknown that we have to find out. Okay, the value of alpha for which the angular momentum about the origin is conserved. Conserved, angular momentum conserved. In order to conserve angular momentum, torque must be 0. So how do we find the torque? Tau equal to R cross F. Okay, and here is the we will find torque here. Okay, right, R cross F. Actually we have to find alpha. Okay, now what we will do now, see, we will find the, see, torque should be 0. Torque 0 means all the components of the torque must be 0. X component of the torque should be 0, Y component of the torque should be 0, Z component of the torque should be 0. We have to evaluate or find out only the value of alpha. So we have to take only the, see, only the component which contains alpha. Okay, now alpha is here. Let's take the Z component or K component. So when we take this K, we have to eliminate the row and column containing that K. So the Z component of the torque will be 2 into 3, that is 6. And this is minus 6 alpha, 6 minus 6 alpha. It will be 6 plus alpha. See, Z component of the torque will be 6 plus 6 alpha. This is equal to 0. Okay, this is 2 into 3, that is 6. And this is minus 6 alpha. 6 minus 6 alpha, that is 6 plus 6 alpha. This is the Z component of the torque. Okay, that should be 0. Means alpha should be minus 1. Then only we will get this one equal to 0. Okay. Actually, you need not find all, you need not completely evaluate this R cross F. Means we have to find out only the value of alpha. For that, you have to find out only the Z component of the torque. Now children, let's see the next question. A solid cylinder of mass 50 kg and radius 0.5 meter is free to rotate about the horizontal axis. A massless string is wound round the cylinder with one end attached to it and the other hanging freely. Tension in the string required to produce an angular acceleration of 2 revolutions per second square. Usually the angular acceleration is expressed in radians per second square. But here it is expressed in revolutions per second square. 2 revolutions per second square. See, in each revolution, angle described is 2 pi radian. So in 2 revolutions, the angle described will be 2 into 2 pi means 4 pi radian. So 2 revolutions per second square means it will be 4 pi radians per second square. Okay, so we have alpha equals 4 pi radians per second square. As it is a solid cylinder, its moment of inertia is mr square by 2. Mass is given 50 kg and radius is half meter. So moment of inertia is 50 by 8. Okay, now suppose the tension in the string is capital F. This is the case. See, this is the side view, means as you view the cylinder from one side, see, this will be the case. And this is the tension in the string, capital F. Okay, the perpendicular distance from the axis is capital R. So the torque will be force into perpendicular distance, means tau we can write Fr, and it is equal to I alpha. So F, that we have to find out. Okay, so that will be I alpha divided by R. Okay, so this implies force will be I alpha divided by R. See, the moment of inertia we have 50 by 8. Okay, and alpha we have got 4 pi and radius is 0.5. Okay, this 0.5 into 8, that will be 4, and this 4 can be cancelled. It will be ultimately 50 pi. Okay, so 50 pi means it will be 157. Okay children, let's see what we have next. Okay, this is a beautiful question. A rod PQ of mass m and length L is hinged at NP. The rod is kept horizontal by a massless string tied to the point Q as shown in figure. When the string is cut, the angular acceleration of the rod is. See, the rod is hinged at these points. Okay, say when we cut this string, see, it will rotate under the effect of the weights. See, the torque due to the weight of the rod will be, see, this is the axis. Okay, from the axis to the line along which the weight is acting, the perpendicular distance is L by 2, and so the torque will be tau equal to mgL by 2. As the rod is rotating about this axis, passing through its one of its ends and perpendicular to its length, its moment of inertia will be ml square by 3. Okay, so tau equal to mgL by 2 and I moment of inertia ml square by 3. So alpha will be tau by I. So mgL by 2 divided by ml square by 3. So it is 3g by 2l. 3g divided by 2l. This is the correct option. Okay, now let us see what we have next. Two discs are rotating about their axis, normal to the discs and passing through the centers of the discs. Disc D1 has 2 kg and mass 0.2, 2 kg mass and 0.2 meter radius and initial angular velocity 50 radians per second. Disc D2 has 4 kg mass and 0.1 meter radius and initial angular velocity 200 radians per second. The two discs are brought in contact face to face with their axis of rotation coincident. The final angular velocity of the system will be. See, this is similar to a case. Suppose a body of mass m1 is moving with a velocity u1 and another body of mass m2 is moving with a velocity u2. These two bodies collide and stick together. Their common velocity v will be m1 u1 plus m2 u2 divided by m1 plus m2. Total linear momentum is conserved. Similarly, here total angular momentum will be conserved. Okay, now let us see I1, moment of inertia of the first disk, that is mr square by 2. Mass is 2 kilogram. Radius is 20 centimeter or 0.2 meter. So mr square by 2 will be 0.04. Moment of inertia of the second disk, it is mass is 4 kilogram. Radius is 10 centimeter or 0.1 meter. So mr square by 2 we will get 0.02. Omega 1 50 radians per second and omega 2 is 200 radians per second. Okay, now one disk is rotating, second disk is also rotating independently. Now the second disk is taken and it is gently placed over the first disk. Okay, so the two disks after some time will attain a common angular velocity that we have to find out. Okay, and it is given by I1 omega 1 plus I2 omega 2 divided by I1 plus I2. So we have 0.04 into 50, 0.02 into 200 divided by 0.04 plus 0.02. Okay. Now see, in the numerator we can take 100 as a common factor, this 50 and 2 from this. Okay, so 100 into, okay, in this first term what remains 0.02, 0.02 plus, and in the second term if we take 100 out, so 2 remains here, 2 into 0.02 will be 0.04. okay, divided by, see in the denominator what do we have, it is 0.06. okay, now this one and this one can be cancelled. Ultimately we will get 100 radians per second. Okay, so this is the answer, 100 radians per second. Now let's try what we have next. When a mass is rotating in a plane about a fixed point, its angular momentum is directed along the axis, because angular momentum is an axial vector. Line perpendicular to the plane of rotation, that is the axis. Line perpendicular to the plane of rotation, that is the axis. Okay, now let's try the next question. ABC is an equilateral triangle with O as its center. F1, F2 and F3 represent three forces acting along the sides AB, BC and AC respectively. If the total torque about O is 0, the magnitude of F3 is. Total torque or turning effect about O is 0. Now suppose this is fixed at O, and see this is F1, this is the line along which F1 is acting. So if we fix at this point O and F1 is applied, it provides a counterclockwise turning effect. Okay, and F2 also provides a counterclockwise turning effect. So the turning effect due to F1 and F2 are along the same direction, but due to F3 it provides a clockwise turning effect. Okay, so the torque due to F1, that is Rf1, torque due to F2, that is Rf2, both are in counterclockwise direction, while the torque due to F3 is in clockwise direction. So see these two torques in the counterclockwise direction that I have taken positive, this is in the clockwise direction that I have taken negative. Okay, so we will get F3 equal to F1 plus F2. Okay, so F3 will be F1 plus F2. Okay, now see this is the centroid O, and all the three sides are at equal distance from the centroids. Okay, now let's see the next question. See, we have a force that is given in component form, and position vector is also given in component form, and we have to find the torque. Okay, so torque equals R cross F. Okay, see these are the components of R and these are the components of F. Okay, now we have to evaluate this determinant. If we evaluate it using this first row, okay, so the first element is this I cap. Okay, so we have to eliminate the row and the column containing that first element I cap. Okay, so what do we get? This is I cap into, if we eliminate this column and row, this is 3 into 5, that is 15, and 1 into 1, that is 1, 15 minus 1, that is 14. Okay, so it is 14 I cap. Next, see we have to take this J. When we take this J, we have to eliminate the row and column containing J. Okay, so this will be 7 into 5, that is 35, minus 3 into 1, that is minus 3. 35 minus minus 3, that is 38. But this j we have to take negative. Okay, so minus j into 38, that is minus 38j. How do we decide whether this is to be taken as positive or negative? Now see, this I belongs to the first row and first column. Okay, then if an element is in the rth row and cth column, or see R is the row number and C is the column number, then you have to evaluate this minus 1 raised to R plus C. Okay, in case of this I cap, that is an element in the first row. See, this is first row and this is first column. Okay, so R is 1 and C is also 1. 1 plus 1, that is 2. Minus 1 raised to 2, that is plus 1. So I have taken this I as positive. And what about this J? It is the element in the first row and second column. So R is 1 and C is 2. So 1 plus 2, that is 3. Minus 1 raised to 3, that is minus 1. So this J is to be taken as negative. Okay, then this K, that is the element in the first row and third column. Okay, so R equal to 1 and C equal to 3. So R plus C will be 1 plus 3, that is equal to 4. So minus 1 raised to 4, that is plus 1. Okay, minus 1 raised to 4 is plus 1. So this is to be taken as positive. So plus K. When we take this K, we have to eliminate the row and column containing K. So this is 7 and this is minus 3 into 3, minus 9. 7 minus minus 9, that is 7 plus 9, that is equal to 16. So 16K. So 14I minus 38J plus 16K. So this will be the correct option. Okay. Now children, let's see the next question. A circular platform is mounted on a frictionless vertical axle. Its radius r equal to 2 meter and its moment of inertia about the axle is 200 kilogram meter square. It is initially at rest. Okay. A 50 kilogram man stands on the edge of the platform and begins to walk along the edge at a speed of 1 meter per second. So the man is moving in a circular path of radius 2 meter with a linear speed 1 meter per second. Okay, time taken by the man to complete 1 revolution. Okay. Now see, consider the platform as one body and its moment of inertia is 200 kilogram meter square. Man as the second body, it can be considered as a point object. Okay, and is moving in a circle of radius 2 meter. Okay, so its moment of inertia will be mr square when it is considered as a point mass. Mass is 50 kilogram and radius or perpendicular distance from the axis is 2 meter. So it is also 200 kilogram. So there are kilogram meter square. So there are two bodies with the equal moments of inertia. Moment of inertia of the platform is 200. Moment of inertia of the man is also 200. So as the man walks over the edge of the platform, there is no external torque acting on the system. Initially the system is at rest, so its angular momentum is 0. As the man walks over the edge, as there is no external torque, angular momentum should remain as 0. Means I1 omega 1 angular momentum of the man disk and I2 omega 2 angular momentum of the man. So this is the total angular momentum that should remain as 0. Okay, so I1 omega 1 equal to minus I2 omega 2. That negative sign is only to show that these two angular momenta should be in opposite direction. Okay, so omega 1 by omega 2 angular velocities of the platform and the man. Okay, that is equal to minus I2 by I1, that is equal to minus 1. Means as the man moves in one direction, say counterclockwise, then the platform should be moving in the opposite direction, that is clockwise, with equal angular speeds. Okay, so omega 1 and omega 2 will be equal and opposites. Omega 2 angular speed of the man, as he moves with a speed 1 meter per second in a circle of radius 2 meter, his angular speed will be 1 by 2, that is equal to 0.5 radians per second. So the platform will be rotating in the opposite direction with the same angular speed 0.5. So the relative angular velocity will be 0.5 minus 0.5. that is equal to 1 radians per second. Okay, as the man completes one revolution, okay, so the relative displacement will be, angular displacement will be 2 pi radian. So the time required will be relative displacement divided by relative angular velocity. Relative angular displacement by relative angular velocity. So 2 pi divided by 1, that is equal to 2 pi seconds. So this must be the answer. Okay. Now let us see what we have next. Instantaneous angular position of a point on a rotating wheel is given by the equation theta. Angular displacement, instantaneous angular displacement is given 2t cube minus 6t square. Torque on the wheel becomes 0. Okay, see, when torque equal to 0, angular acceleration will be 0. So we have to find the time when the angular acceleration becomes 0. So if you differentiate it, that angular displacement with respect to time once, you will get angular velocity. If you differentiate it once more, you will get angular acceleration. Okay, find the angular acceleration, equate it to 0 and then find the time. Okay, we have theta equal to 2t cube minus 6t square. Angular velocity d theta by dt, that will be 2 is constant and differential of t cube will be 3t square. So 2 into 3t square, that is 6t square. Okay, and here we have 6 is constant and t square differential will be 2t. 6 into 2t, that is 12t. Okay, let's differentiate once more. Okay, 6 into differential of t square will be 2t. So 6 into 2t, that is 12t. And 12 is constant, differential of t will be 1. So 12t minus 12, that is the angular acceleration. It will become 0 when t equal to 1 second. So the torque will be 0 when t equal to 1 second. Okay, so this must be the correct option. Okay, t equal to 1 second. Now let's see what we have next. Okay, this is a beautiful question. Okay, now see, in linear mechanics or in see Newton's laws of motion or in work energy and power. See, suppose two bodies are moving. Okay, two bodies of masses, say m1 moving with velocity u1, another body of mass m2 moving with velocity u2. They collide and after collision they stick together and move together with a common velocity, say v. Then there will be some, see, loss of kinetic energy. And that loss of kinetic energy, children please listen, half, then half, okay, loss of kinetic energy is half, okay, then m1 m2 divided by m1 plus m2, okay, and u1 minus u2 whole square. Okay, now see, suppose a capacitor is charged to C1, charged to voltage V1, another capacitor C2 charged to voltage V2. These two are connected together in parallel. They will attain a common voltage. The loss of energy delta U, loss of energy delta U, half C1 C2 by C1 plus C2. Then V1 minus V2 whole square, where V1 and V2 are not velocities, voltages, V1 and V2. Okay, means this form, okay, this form is very important. Here we have two rigid bodies with the moments of inertia, say I1 and I2. And they were rotating with the angular velocities omega 1 and omega 2 independently. Body of moment of inertia I1 is rotating with angular velocity omega 1. Another body of moment of inertia I2 is rotating with angular velocity omega 2. Here we have two circular discs. Now suppose I have taken this second disc and gently placed over the first. After some time they will attain a common angular velocity. There will be some energy loss, and that energy loss also will have the same form. Okay, and it is being given by half I1 I2 by I1 plus I2 into omega 1 minus omega 2 whole square. Okay, so this is here we have see, it is given as IB and IT, IB and IT. Okay, a circular disc of moment of inertia IT is rotating in a horizontal plane about its symmetry axis with a constant angular speed omega I. Another disc of moment of inertia IB is dropped coaxially onto the rotating disk, means the second disk was initially at rest. Omega 2 is 0. Okay, so you can put this omega 2 and omega I will be, see, omega 1 will be equal to omega I. So this will be, that is very simple, half IB IT divided by IB plus IT. Okay, so this must be the correct option. Now let's see the next question. If F is the force acting on a particle having position vector R and tau be the torque on this force about the origin, then tau equal to R cross F. So tau must be perpendicular to R, tau must be perpendicular to F. Okay, tau perpendicular to both R and F. Okay, so see the second option, R dot tau, R and tau are perpendicular, so dot product will be 0. And F dot tau, F and tau are perpendicular, so the dot product will be 0. So this must be true, this must be true. And R dot tau greater than 0 cannot be 0, cannot be greater than 0. And F dot tau, this should be 0. Okay, and here it is given that F dot tau less than 0. No, it is equal to 0. Okay, and here R dot tau equal to 0, that's fine. F dot tau not equal to 0, that is wrong. And here we have R dot tau not equal to 0, that is wrong. Okay, F dot tau equal to 0, that's fine. Okay, now let's see the next question. A particle of mass m moves in the xy plane with velocity v along the straight line AB. Okay, see, here is the point A and here is the point B. Okay, this is the straight line AB and the particle is moving along that line. Okay, if the angular momentum of the particle with respect to origin O is LA when it is at A and LB when it is at B, then see, when the particle is moving along this line, angular momentum is linear momentum into lever arm. Lever arm means perpendicular distance from the reference point or from the axis to the line along which the linear momentum is acting. See, this is the line along which the particle is moving. This is the line along which its linear velocity is directed. This is the line along which its linear momentum is acting. So when the particle is here, or when it 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 is here, as long as the particle is on that straight line, there is only one lever arm, there is only one perpendicular distance from the axis to that line. See, if you draw a line like this, it is, see, the length of that line is not the perpendicular distance. If you draw a line like this, the length of that line is not the perpendicular distance, because this does not meet at 90 degree. This line also does not meet at 90 degree. See, there is only one line from the axis that meets this line at 90 degree. See, that is being shown here. Okay, so wherever be the particle on this straight line, the lever arm is this much smaller. So the angular momentum LA and angular momentum LB must be equal. Okay, so LA must be equal to LB. Okay, now let us see what we have next. A tube of length L is filled completely with an incompressible liquid of mass capital M and closed at both the ends. The tube is then rotated in a horizontal plane about one of its ends with a uniform angular velocity omega. The force exerted by the liquid at the other ends is, force exerted by the liquid at the other ends is. Okay, now see, mass is distributed uniformly. Okay, and mass per unit length, okay, that is lambda, represented by lambda, it is equal to m by L. Okay, now consider a small element of length dx, okay, at a distance x from the axis. See, at a distance x from the axis, I have taken a small element and its length is dx. Mass per unit length is lambda. So mass of an element whose length is dx will be lambda dx. And what is lambda? It is m by L. Lambda dx will be m by L into dx. So this much is the mass of this small elements. As the tube rotates about this fixed axis, that element will be moving in a circle. Whenever a particle is moving in a circle, there must be an unbalanced force, a resultant force directed towards the center. Suppose the liquid on the left side of this element exerts a force like this, and the liquid on the right side of that element exerts a force like this. Resultant force must be towards the center. So the force acting from left to right, okay, that is F, and the force acting from right to left must be more stronger, F plus dF, because then only the resultant force will be directed towards the center. Okay, so the resultant force, that is dF, because see, along this direction F and in the opposite direction dF. Okay, F plus dF. So the resultant force will be dF, right? And that provides the centripetal force. See, this much is the mass of the element, m. Next we have to take the radius of the circle in which the element is moving, that is x, mr omega square. Okay, so that much is the force acting on an element at a distance x. See, we have to find the force on all such elements from x equal to 0 to x equal to L. Okay, that will give you the resultant force, capital F, integral dF, m by L omega square x dx, to be evaluated from 0 to L. See, in which m omega square L is constant, that we can take outside, and when x is integrated we will get x square by 2. Okay, when it is evaluated from 0 to L, we will get L square minus 0 square divided by 2. So ml omega square by 2 ultimately, ml omega square by 2. Now let's see what we have next. Two bodies have their moments of inertia I and 2I respectively about their axis of rotation. If their kinetic energies of rotation are equal, then their angular momenta will be in the ratio. See, this is linear momentum in terms of mass and translational kinetic energy. See, corresponding relation in rotational motion, that is angular momentum L equal to under root 2 into moment of inertia into rotational kinetic energy, E with the suffix R. Here we have two bodies with equal kinetic energy, rotational kinetic energy, but their moments of inertia are different. Which one will have greater angular momentum, or we have to find the ratio of the angular momentum. See, we have two bodies. For both the bodies, this ER is the same and 2 is also same. So let us say angular momentum directly proportional to the moment of inertia. So L1 by L2 will be root of I1 by I2, and that will be root of I by 2I or 1 by root 2. Okay, so it is 1 is to root 2. Okay, now let's see what we have next. A wheel having moment of inertia 2 kg meter square about its vertical axis rotates at the rate of 60 rpm about this axis. See, frequency is given as 60 rpm, 60 revolutions per minute, or 60 revolutions in 60 seconds. So 1 revolution per second, or it is 1 hertz. And angular velocity will be 2 pi into frequency, so it is 2 pi into 1 or 2 pi radians per second. Okay, and the torque which can stop the wheel's rotation means the final angular velocity is 0. Okay, and it is to be done, or the wheel is to be brought to rest in 1 minute, means the time is 60 seconds. Alpha, we have delta omega by delta t, angular acceleration. Final angular velocity is 0, initial angular velocity is 2 pi, and that change takes place in 60 seconds. So the angular deceleration is minus pi by 30. Okay, tau equal to I alpha, and moment of inertia it is given as 2 kg meter square. So 2 into pi by 30, that is pi by 15 Newton meter. Pi by 15 Newton meter. Okay, now let's see the next question. Consider a system of two particles having masses m1 and m2. Okay, if the particle of mass m1 is pushed towards the center of mass of particles through a distance d, By what distance would the particle of mass m2 move so as to keep the center of mass of the particles at the original position? What does it mean? Center of mass does not move. Displacement of the center of mass is 0. Okay, see, this is the formula for the displacement of the center of mass. Okay, that SCM, displacement of the center of mass, is 0, means this numerator should be 0. Okay, so m1 s1 plus m2 s2 equal to 0, and s2 must be equal to minus m1 by m2 into s1. That negative sign is to show that displacement of the two bodies must be in opposite direction. Displacement of the first body is given as d. So s1 equal to d. So s2 will be m1 d by m2. m1 d by m2. Okay. Next, see, a round disk of moment of inertia I2 about its axis perpendicular to its plane and passing through its center is placed over another disk of moment of inertia I1 rotating with an angular velocity omega about the same axis. So initially only one of the disks is rotating. The disk of moment of inertia I2 is at rest. So the total angular momentum initially I1 omega. Finally I1 and I2 are placed together. So the total moment of inertia will be I1 plus I2. And angular velocity, say it is omega dash. See, in this process angular momentum will be conserved. This is the initial angular momentum and this is the final angular momentum. So omega dash will be I1 divided by I1 plus I2 into omega. Okay, I1 divided by I1 plus I2 into omega. So this is the correct option. Now let us see what we have next. A thin circular ring of mass capital M and radius r is rotating about its axis with a constant angular velocity omega. Initially only the ring is rotating. Okay. Now 4 objects each of mass m are kept gently to the opposite ends of two perpendicular diameters. Okay. Then what would be the final angular velocity? Initially only the ring is rotating. So the initial moment of inertia will be that of the ring, that is mr square, and angular velocity omega. So initial angular momentum will be mr square omega. Finally, there are 4 point objects kept on the ring. So the moment of inertia will be moment of inertia of the ring plus moments of inertia of these 2 point objects. See, the moment of inertia of a point object is mass into square of its perpendicular distance from axis. So the moment of inertia of each point object will be mr square. Such 4 objects are there. So total moment of inertia of these 4 point objects will be 4 mr square. And the moment of inertia of the ring will be capital M into r square. So finally, the total moment of inertia, this is the moment of inertia of the ring and this is the moment of inertia of the 4 point objects. So this is the total moment of inertia and final angular velocity omega dash. So omega dash will be m omega divided by capital M plus 4m, m omega divided by capital M plus 4m. This is very simple, but it is a typical question. Many times the same or similar questions appeared in this NEET question paper. So you have to understand this. Okay, similar question you can expect always. A disk is rotating with angular velocity omega if a child sits on it. What is conserved? Only angular momentum will be conserved. Angular momentum will be conserved. Okay. Now let's try the next question. A constant torque of 1000 Newton meter turns a wheel of moment of inertia 200 kilogram meter square about an axis through its center. Its angular velocity after 3 seconds. See, F delta T equal to M delta V. Okay, corresponding relation in rotational mechanics, that is tau delta T, it's the angular impulse, that is equal to change in angular momentum. Okay, I delta omega. So delta omega, that is change in angular velocity. Okay, so final angular velocity omega minus initial angular velocity 0, that is delta omega. It must be equal to tau delta T by I. Tau is given as 1000 Newton meter and time is 3 seconds. Moment of inertia is 200. 1000 divided by 200 will give you 5. 5 into 3 will give you 15. Okay, this is 15. Now let's try the next question. A weightless ladder 20 feet long rests against a frictionless wall at an angle 60 degree from the horizontal. 150-pound man is 4 feet from the top of the ladder. A horizontal force is needed to keep it from slipping. Choose the correct magnitude of the force from the following. Okay, that horizontal force is usually applied here. Okay, at the bottom. That capital F we have to find out. Now see, the ladder is in equilibrium. See, there is a man weighing 150 pound at a distance 4 feet from the top. Okay, see, the total is 20 feet. And see, from this top to here is the man standing, and his weight is 150 pound. Okay, that is acting vertically down. Okay, that is one force acting on the ladder. Then the normal reaction exerted by the floor. Okay, and see the horizontal, see normal reaction exerted by the wall. As the wall is vertical, reaction exerted by the wall will be normal to it, means along the horizontal. Okay, now see, we have applied a horizontal force at the bottom, and see, this floor exerts a normal reaction directed vertically up. Ladder is in equilibrium. So the resultant force in the vertical direction should be 0. What are the forces acting along the vertical? 150 pound and this normal reaction. Okay, so this normal reaction should be equal to 150. Then only, see, this and this will balance. Similarly, there are two forces acting along the horizontal. One is the force, this reaction exerted by the vertical wall, and the other is the external force applied here. Actually, we want to find out this capital F, but this will be equal to the normal reaction exerted by the wall. Okay, now see, if this is F, here is the normal reaction, say N2, this also will be equal to F, and say this is N1, right? Okay, now N2, that is equal to capital F, that we have to find out. Okay, we have considered the translational equilibrium. Equilibrium along the horizontal direction and equilibrium along the vertical direction. Okay, now let us take the rotational equilibrium, or let us find the turning effect about this point. Okay, I am taking the turning effect about this point because, see, altogether there are 4 forces, of which 2 of the 4 forces are passing through this point. So if you find the turning effect about this point, the turning effect about these two, turning effect due to these 2 forces will be 0. If you take the turning effect at this point, so you will get a simple relation. Okay, so you have to choose the point of reference where maximum number of forces are acting. Here we have only 4 forces and 2 of the forces are acting at this point. So let us take the moment about this point, torque about this point. Okay, so if we fix the ladder at this point and apply a force like this, it will tend to turn the ladder like this, means it is clockwise. And if you fix the ladder at this point and apply a force like this, it will tend to turn the ladder like this, counterclockwise. These 2 torque or turning effects should be equal. Okay, now first let us find this turning effect F into, this is the perpendicular distance, that will be 20 sine 60. Okay, this one 20 sine 60. So F into 20 sine 60. Next, see the turning effect due to this force 150. Okay, this much will be the turning, will be the perpendicular distance, will be this much. Okay, and that will be equal to, see, this is 16 and this will be 16 cos 60. 16 cos 60. Okay, 150 into 16 cos 60, right? We have to find out this capital F. So sin 60 will be root 3 by 2 into 20, that is 10 root 3. And on the right side we have 150, 16 cos 60 will be 1 by 2. Okay, cos 60 will be 1 by 2, that is 1 by 2. Okay, see, 16 into cos 60, that is 16 into 1 by 2, that is equal to 8. That 8 I have written here, this 8. Okay, next we have 150. that we can write 5 into 3 into 10, right? 150 can be splitted as 5 into 3 into 10. 5 I have written here, 10 also written here. Now I have to write 3. 3 can be splitted as root 3 into root 3. Okay, because I have here a 10, that 10 and this 10 can be cancelled. Then I have a root 3 and this root 3 can be cancelled. So finally we will get this 5 into 8, that is 40 root 3 pounds. Okay, 40 root 3 pounds. And root 3, that is 1.732. Okay, 1.732 into 40. Okay, means 17.3 into 4. Okay, take it at 17.5 into 4 means you will have to double it 2 times to multiply by 4. 17.5 into 2 will be 35. Again into 2 will be 70. So approximately 70 pounds. Okay. We have the beautiful answer. Approximately 70 I have told you, no? Because it is actually 17.3 but I have taken 17.5. Okay. So the actual answer will be slightly smaller than what we are getting. Okay, we have got 70. Answer will be slightly smaller than 70. So it must be 69.2. A couple produces no motion, purely linear, purely rotational motion. Means couple means two equal and opposite forces. Resultant force will be 0. Only there will be a turning effect. Okay. Now let's angular momentum of a body with a mass m, moment of inertia I and angular velocity omega will be I omega. Okay, this one I omega. Okay, and next angular momentum is an axial vector. Angular momentum is an axial vector. Okay, now see a particle of mass m equal to 5 units is moving with the uniform speed v equal to 3 root 2 in the XOY plane along the line y equal to x plus 4. Okay, y equal to x plus 4. So the particle is moving along that line. Can you draw that line? Of course. Okay, so see that line, see you can find the point where that line cuts the y-axis. How do you get that point? Put x equal to 0. When you put x equal to 0, you will get y equal to 4. Means the line will be cutting the y-axis at y equal to 4. Okay, so this is x-axis, this is x-axis and this is y-axis. Okay, so y equal to 4, this point, that is a point on the straight line. Where do that line cuts the x-axis? How do you get that? Put y equal to 0. When you put y equal to 0, you will get x plus 4 equal to 0, then x equal to minus 4. That is the point at which the line cuts the x-axis. Okay, this is positive x-axis and this is negative x-axis. So this is the point, this is another point on the line. So we have got 2 points. So simply join these 2 points, you will get the required line. Okay, the particle is moving along this line. So its linear momentum is acting along this line. We have to find the perpendicular distance from the origin to that line. Okay, so this broken line is the perpendicular distance, broken line. Now children, we have this right triangle here, no? We have a right triangle here. Okay, and see this angle is 45 degree, this angle is also 45. Okay, because see this is 4 units and this is 4 units, so this must be 45 and this must be 45. Okay, now see this angle, see this we have, see this one. Okay, this one we have 90 degree, this is 45, this is 45. So it is an isosceles right angled triangle. Which one? This one, an isosceles right angled triangle in which this is the hypotenuse. Okay, and it is equal to 4 units. Okay, so this will be, this is 4 by root 2 and this is also 4 by root 2. So 4 by root 2 is the perpendicular distance. Okay, 4 by root 2 is the perpendicular distance from the origin to the line along which the particle is moving, or to the line along which the linear momentum is acting. Okay, now let us find the angular momentum, that is P means mass into velocity. Linear momentum, mass is 5 units and velocity is 3 root 2. And the lever arm, that is the perpendicular distance that we have got 4 by root 2. This root 2 and root 2 we can cancel. See what remains, 5 into 3, that is 15 into 4, it will be 60 units. Okay. Now children, we have the equation of the straight line along which the particle is moving, that is given as y equal to x plus 4. Y equal to x plus 4. It can also be written as, see, take this y to the right, you will get x minus y plus 4 equal to 0. Okay, x minus y plus 4 equal to 0. If you have studied mathematics, you must be knowing that if this is the equation of a straight line, and if you want to find the perpendicular distance from say x1 y1 to x1 y1 to this line, what would be that perpendicular distance? X1 minus y1 plus 4 divided by root of 1 square plus minus 1 square. Okay, but here we have to find the perpendicular distance from origin. Means here we have to put 0, here also you have to put 0. So in the numerator only 4 remains, and in the denominator there will be root of 1 square plus minus 1 square, 1 square plus minus 1 square. So you will get 4 by root 2. Or perpendicular distance you can find either by using this one, or like this you can find. However you find the perpendicular distance, you will get the angular momentum as 60 units. Okay. Now let's try what we have next. See, solid homogeneous sphere of mass m and radius r is moving on a rough horizontal surface. Okay, partly rolling and partly sliding. During this kind of motion, the sphere, see, we have a sphere like this, okay, and it is moving over a horizontal rough surface. What are the forces acting on that sphere? Okay, the forces acting on that sphere are, its weight will be acting vertically down. Okay, and see, the normal reaction will be acting like this. Okay, now suppose it rolls like this. Okay, the friction will be acting like this, friction. Okay, friction. See, this is the point of contact. All the 3 forces are passing through that point. All the 3 forces. So the torque about that point due to any of these forces will be 0. How do you find the torque? Force into lever arm or perpendicular distance. Now see, if the weight is acting like this, then the perpendicular distance will be this much. Okay. Now if the weight is acting like this, then the perpendicular distance will be this much. But here the weight is acting like this, so the perpendicular distance will be 0. No torque due to the weight. Okay. Okay. Now see, if the normal reaction is acting like this, this will be the perpendicular distance. But here the normal reaction is acting like this, so the perpendicular distance about or from that point will be 0. Okay, so there is no torque due to the normal reaction. See, if this friction had been acting like this, this is the perpendicular distance. Okay. Now see, if this is the line along which the friction is acting, then from this point, see, this much will be the perpendicular distance. But here the friction is acting like this, so perpendicular distance from the point of observation will be 0. So there is no torque due to any of these forces about this point of contact. So resultant torque 0, angular momentum will be conserved. Okay. So total kinetic energy is not conserved. Angular momentum of the sphere about the point of contact with the plane is conserved. Okay, so only this one will be true. And only the rotational kinetic energy about the center of mass is not conserved. Angular momentum about the center of mass is also not conserved, because see, this is the center of mass. Weight is passing through it, no torque due to the weight about the center of mass. Normal reaction is passing through the center of mass, no torque due to normal reaction about the center of mass. But the friction is not passing through the center of mass. So there will be torque due to the friction. So angular momentum about the center of mass will not be conserved, because there is an unbalanced torque about the center of mass. Okay. Now see the next question, the ratio of the radius of gyration of a solid sphere of mass capital M and radius R about its own axis to radius of gyration of a thin hollow sphere of same mass and radius. Okay, we have a solid sphere and a hollow sphere. See, moment of inertia is mk1 square, that is solid sphere, 2 by 5 mr square, and mk2 square, that is hollow sphere, 2 by 3 mr square. So k1 by k2 whole square will be, if we divide these two, we will get 3 by 5. So k1 by k2 will be root of 3 by 5, or let us say root 3 is to root 5. So this will be the correct option, root 3 is to root 5. Now see what we have next. The energy of 484 joule is spent in increasing the speed of a flywheel from 60 rpm to 360 rpm. The moment of inertia is, see, work done equal to change in kinetic energy. See, final kinetic energy will be half I omega f, omega final square, minus half I omega I square, where omega I is the initial angular velocity. See, initial frequency is 60 rpm, means 60 by 61 hertz. Okay, and the final frequency is 6 times, so it must be 6 hertz. Okay, and omega is 2 pi f. So final angular velocity will be 2 pi into final frequency, that is 6 hertz. Initial angular velocity will be 2 pi into initial frequency, that is 1 hertz. See, we have 2 pi common here. Okay, 2 pi square means 4 pi square we can take outside. So what remains here? Here we will have 6 square, and here we will have 1 square. So 6 square minus 1 square, that is 35. 4 by 2, that is 2. Okay, 2 into 35, that will be 70. Okay, and so W will be equal to, work done will be equal to I into 70 pi square. Okay, and I will be W by 70 pi square, and W, work done, is given as 484 joule. Okay, now see, if you take that pi square approximately equal to 10, you will get 700 in the denominator. Okay, and 484 in the numerator. Or we can write this as see, 4.84 divided by 7 approximately, because I have taken that pi square as 10. Okay, now you must be knowing 7 into 7 is 49. 7 into 0.7 is 4.9, and here we have 4.84. So 4.84 must divided by 7 must be nearly equal to 0.7. So we will get an answer somewhere near to 0.7. Okay, we have the beautiful answer 0.7. Right? Now let's see the next question. The ratio of the radius of gyration of a thin uniform disc about an axis passing through its center. Okay, means this is the axis. Okay, about an axis passing through its center and normal to its plane. This is the first axis. Okay, and the second axis is diameter. Okay, and see, and normal to its plane to the radius of gyration of the disc about its diameter. Okay, now see, suppose this is the which one, ratio of the radius of gyration of a thin uniform disc. Okay, this is the disc and this is a diameter. The moment of inertia of the disc about that diameter, let it be capital I. This is an identical diameter, so the moment of inertia about this diameter also will be capital I. Then by perpendicular axis theorem, see, the moment of inertia about this axis normal to the plane and passing through center, it will be 2I. This is the first axis and diameter is the second axis. Okay, so the moment of inertia about the first axis, I1 equal to 2I, and moment of inertia about the second axis I2 equal to I. In general, moment of inertia I equal to mk square. Okay, so let us say k directly proportional to square root of the moment of inertia. So k1 by k2 will be under root I1 by I2, and it is under root 2I divided by I, or it will be root 2 is to 1. Okay, so this will be the correct answer. Okay, now let us see what we have next. From a circular ring of mass capital M and radius capital R, an arc corresponding to 90-degree sector is removed. See, if we consider this ring into 4 identical parts, see the moment of inertia about this axis, that is mr square. Okay, and all the 4 quarters are identical. Okay, and the moment of inertia of each quarter will be mr square by 4. Okay, now we have see here there is 1, okay, here there is 2, and this is 3. So 3 parts. Okay, and the total moment of inertia will be 3 by 4 mr square. 3 by 4 mr square. And here it is given that k times mr square means k should be 3 by 4. Okay, so this is 3 by 4. Next is solid sphere is rotating freely about its symmetry axis in free space. The radius of sphere is increased by keeping its mass same. Okay, which of the following physical quantities will remain constant for the sphere? Only the angular momentum. Okay, now 2 discs, same question we have discussed earlier. Okay, the loss of kinetic energy will be half. Okay, we have this formula I1 I2 divided by I1 plus I2, and here we have 2 identical discs, each of moment of inertia capital I. Okay, so this will be I square by 2I, or it will be I by 2. So I by 4 omega 1 minus omega 2 whole square. Okay, now from a disc of radius capital R and mass m, a circular hole of diameter capital R. Diameter capital R means radius R by 2. See, from a disc of radius capital R, another disc of radius R by 2 is removed. Okay, like this. What is the moment of inertia of the remaining part of the disc about a perpendicular axis passing through the center? Okay, now see, mass is directly proportional to area. See, the area of this removed part will be 1/4 of the total area. So if capital M is the mass of the original disc, okay, original disc capital M, then the mass of this removed part will be m by 4. Okay, now see the moment of inertia of the remaining part. Moment of inertia of the remaining part is the moment of inertia of the original disc minus moment of inertia of the removed disc. What is the moment of inertia of the original disc? Let it be I1. The moment of inertia of the removed smaller disc, let it be I2. So the moment of inertia of the remaining part will be I1 minus I2. Okay, I1, see the moment of inertia of the original disc, that is mr square by 2, and moment of inertia of the removed part means this smaller disc. Okay, about this axis. Okay, see moment of inertia of a disc about an axis. See, this is the moment of inertia of a disc about an axis, normal to its plane and passing through its center, it is mr square by 2. And here is the axis passing through the rim and normal to its plane. Okay, let it be capital I. Okay, so by parallel axis theorem, I equal to ICM plus MA square. ICM is mr square by 2 and MA is R. So see here A equal to R. Okay, so this will be I equal to, this ICM is mr square divided by 2 plus mr square. Okay, so the moment of inertia about this axis will be 3 by 2 mr square. Moment of inertia of a disc about an axis passing through the rim, through the edge and normal to its plane, that is 3 by 2 mr square. 3 by 2 mr square. Now see, but here the removed disk is of mass m by 4. So 3 by 2 instead of m we will have to put m by 4. 3 by 2 m by 4 and the radius is r by 2, not r. Okay, so 3 by 2 instead of mass we have to put m by 4 and for radius we have to put r by 2. Okay, so this will be, here we have r by 2 whole square means it is r by 4 into m by 4, that is mr square by 16. Yeah, mr square by 16. So 3 mr square by 32. Okay, 3 mr square by 32. So here we will have to subtract mr square by 2 minus 3 mr square by 32. Okay, mr square by 2 is common. When it is taken out, the first term will be 1 and the second term will be 3 by 16. 1 minus 3 by 16 will be 13 by 16. Okay, so it will be 13 mr square by 32, 13 mr square by 32. 13 mr square by 32. Okay, now let us see what we have next. Moment of inertia of the system. Identical spherical shells. Okay, this is the axis. See, the axis is a diameter of the first shell. So its moment of inertia will be 2 by 3 mr square. And the axis is a tangent of the second and third shell. Okay, moment of inertia about a tangent will be 2 by 3 mr square plus mr square. Okay, see, moment of inertia, this is the shell. Okay, and we want to find the moment of inertia about this tangent. We have to apply the parallel axis theorem. This is the axis about which we have to find out the moment of inertia. Consider an axis parallel to the given axis and passing through the center of mass. That will be a diameter. So this is I with the suffix em. Okay, and this distance a equal to r. So moment of inertia I, see, this I will be equal to ICM plus MA square. ICM means this one, that is 2 by 3 mr square plus MA is r, so it will be mr square, and this is equal to 5 by 3 mr square. 5 by 3 mr square. So moment of inertia of the second disk about the given axis is 5 by 3 mr square. Moment of inertia of the third disk about the given axis is also 5 by 3 mr square. Total moment of inertia will be I1 plus I2 plus I3. Okay, so that will be, here we have 5 by 3 plus 5 by 3, 10 by 3 plus 2 by 3, that is 12 by 3 or 4 mr square. Okay, 4 mr square. Now let us see the next question. The ratio of the radius of gyration of a circular ring and a circular disc of the same mass and radius about an axis passing through their centers and perpendicular to their planes. First is a ring mr square. Second is a disc mr square by 2. Okay, and the moment of inertia, the I1 by I2 will be 2:1. And we have to find the ratio of the radii of gyration. Means K1 by K2 will be under root. Okay, K1 by K2 will be under root I1 divided by I2, or this is equal to root 2:1. Okay, root 2:1 this must be. Okay, now let us see what we have next. The moment of inertia of a uniform circular disc is maximum about an axis perpendicular to the disc and passing through a point which is at maximum distance from the center of mass. This is the central axis. So the moment of inertia will be maximum about an axis passing through a point which is farthest from the center of mass. Okay, and that point is B. Okay, this is the formula to find the moment of inertia. So I equals ICM plus mx square, where x is the distance between the axis and the axis passing through the center of mass. That x will be maximum in case of the axis passing through B. Okay, so this one. Next, the moment of inertia of a thin uniform rod of mass m and length L about an axis passing through its midpoint and perpendicular to its length is I0. its moment of inertia about an axis passing through one of its ends and perpendicular to its length. Again, we have to use the parallel axis theorem. This is the axis passing through its center and perpendicular to its length, and moment of inertia is I0, or here this is I with the suffix em. I with the suffix em. See, what is the formula? I equal to I with the suffix em plus ma square, where a is the perpendicular distance between the two axes. Here it is L by 2. So it must be I0 plus mL square by 4. Means this one. Next, 4 identical thin rods, each of mass capital M and length, forms a square frame. Okay. Moment of inertia of this frame about an axis through the center of the square and perpendicular to its plane is. See, the moment of inertia of this rod about an axis passing through its center is ml square by 12, and about this axis, okay, this axis, it will be ml square by 12 plus m into square of this distance, and that distance is L by 2. So ml square by 12 plus m into L by 2 whole square, ml square by 12 plus m into L by 2 whole square, and it is ml square by 3. So the moment of inertia of one rod with respect to an axis passing through the center of the frame, it is ml square by 3, and there are 4 such rods. So it will be 4 into ml square by 3. So 4 by 3 ml square. Okay, now see, next, a thin rod of length L and mass m is bent at its midpoint into 2 halves so that the angle between them is 90 degrees. The moment of inertia of the bent rod about an axis passing through the bending point and perpendicular to the plane defined by the 2 halves of the rod is ml square by 12 only. See, because with respect to this axis, the orientation of the rod does not change. See, with respect to this axis, this part is perpendicular to the axis. Okay, this part is also perpendicular to the axis. When those two parts are mutually perpendicular, then also see, about this axis orientation does not change. You know what happens actually? See, when it is bent, it will be like this. Like this. Okay, both the parts are identical, and the axis is like this. Okay. So it will be perpendicular. See, this axis is perpendicular to this part as well as this part. Okay. If this part is like this or like this, it does not make any change. So it will be ml square by 12 only. Okay. ml square by 12. Okay. Next. The moment of inertia of a thin uniform circular disc of radius r and mass m about an axis touching the disc at the perimeter and normal to the disc, means passing through the rim and perpendicular to its plane. See, this is an axis passing through the center of mass, and this is a parallel axis. Okay, this moment of inertia we have to find out. Okay, so we have to use the parallel axis theorem, I equal to ICM plus MA square. As this is a thin uniform circular disc, ICM is mr square by 2, so it will be 3 by 2 mr square. 3 by 2 mr square. Okay. The ratio of the radii of gyration of a circular disc about a tangential axis in the plane of the disc and of a circular ring of the same radius about a tangential axis in the plane of the ring. Okay. Now see, this is a disc. Okay. And see, moment of inertia about a diameter. See, moment of inertia about the central axis is mr square by 2. Then the moment of inertia about the diameter will be half of it, mr square by 4. Okay, and this is an axis parallel to the axis passing through the center of mass, ICM. Okay, and this is I. So I equal to ICM plus MA square. So mr square by 4 plus mr square, that will be 5 by 4 mr square. And for a ring, this ICM, about the diameter, it is mr square by 2, and about this axis, it will be 3 by 2 mr square. Okay, I1 by I2 will be, the I1 by I2 will be 5 by 4 into 2 by 3. Okay, that is 5 by 6. Okay, I equal to mk square, and k will be directly proportional to I. So k1 by k2 will be root of I1 by I2. So root 5 is to root 6. Root 5 is to root 6. Okay. Now let us see what we have next. Three particles each of mass m are situated at the vertices of an equilateral triangle ABC of side L. The moment of inertia of the system about AB. See, this is the axis AB. See, the point objects A and B are on the axis. So the moment of inertia of the point object A is 0. Moment of inertia of the point object B is 0. Okay, so the moment of inertia of the point object C, that will be the moment of inertia of the system. Okay, this C being a point object, its moment of inertia will be mr square, means m into square of its distance, perpendicular distance from the axis. See, perpendicular distance from this axis, that is equal to this much. Okay, and that distance will be, see, this is L and this angle is 60 degree. Okay, so this will be L sin 60. L sin 60, and it is L root 3 by 2. Okay, L root 3 by 2. So mass is m and the perpendicular distance is root 3 L by 2 whole square. So it will be 3 by 4 m L square. Now let's see the next question. A ball rolls without slipping. The radius of gyration of the ball about an axis passing through its center of mass is capital K. If radius of the ball be capital R, then the fraction of total energy associated with rotational energy will be. Means we want to find the ratio of rotational energy to the total energy. See, a rolling body possesses translational kinetic energy half mv square as well as rotational kinetic energy half I omega square. This translational kinetic energy is proportional to the square of the radius, and rotational kinetic energy is proportional to square of the radius of gyration. Okay, so we can write translational energy by rotational energy equal to R square divided by K square. Okay, this is the ratio. This is rotational energy, and capital E without any suffix represents the total energy. Okay, so we can write rotational energy divided by rotational plus translational, that is the total energy. Okay, by using the componendo dividendo rule, we can write K square divided by K square plus R square. Okay, so this must be the correct option. Okay, now children, let's see what we have next. A composite disc is to be made using equal masses of aluminum and iron so that it has as high a moment of inertia as possible. This is possible when the surface of the discs are made of iron with aluminum inside. See, a composite disc is to be made by using equal masses of aluminum and iron so that it has high moment of inertia. See, for equal masses of aluminum and iron, see, the volume of iron will be smaller, okay, and volume of aluminum will be more. Okay, so we will get a body with a larger moment of inertia if aluminum is inside and see, iron is outside. Okay, the whole of aluminum is kept in the core and iron at the outer rim of the disc. Okay, alright. So so that more mass will be at maximum distance. Okay, as the moment of inertia is proportional to, or moment of inertia of a point mass is mr square. If the mass is at maximum distance from the axis, the body will have a greater moment of inertia. Okay, now let's see the next question. There is a flat uniform triangular plate ABC. Okay, AB equal to 4 cm, BC equal to 3 cm, and angle ABC equal to 90 degree. The moment of inertia of the plate about AB, BC and CA as axis is respectively Okay. Now see, if the distance of the axis from the center of mass is more, then the moment of inertia about that axis will be more. Okay. Now see the location of the center of mass we can easily find. Suppose this is 0, 0, so this will be 3, 0 and this will be 0, 4. Coordinates of the center of mass are x coordinate is x1 plus x2 plus x3 by 3, that we will get 1, and y coordinate similarly we will get 4 by 3. Okay, and see this is the first axis. See, this is the first axis, and the distance of the center of mass from this axis will be the x coordinate of the center of mass, and that is equal to 1 centimeter. That is the distance of the center of mass from the first axis, and let me represent it as R1. Okay, now this is the second axis, and the distance of the center of mass from the second axis is the y coordinate, and that is equal to 4 by 3, and let me represent it as R2. Okay, and see, this is the third axis. Okay, this is the third axis. You can easily write the equation of this line, and that we will get 4 by 3 x plus y minus 4, and the perpendicular distance from the centroid to this line means perpendicular distance from 1 4 by 3 to this line will be, okay, see this is the formula. Okay, and that we will get 4 by 5, that is the perpendicular distance of the third axis from the centroid or from the center of mass, and that we will get 4 by 5. Okay, and this is 4 by 5 means this is equal to 0.8, and this is equal to 1.33, and this is equal to 1 centimeter. So the distance is maximum in the second case. So I2 will be the greatest. Okay, so after that then R1, so I2 greater than I1 greater than I3. Okay, I2 greater than I1. Okay, so this is true, I2 greater than I1. Then first option, I3 greater than I2, that is false. I3 greater than I1, that is also false. I1 greater than I2, that is also false. Only the second option will be correct. Okay. Now let's see the next question. The moment of inertia of a disk of mass m and radius r about an axis which is tangential to the circumference of the disk and parallel to its diameter. Means it is a tangent in the plane of the body. Okay, now we have to apply the parallel axis theorem. See, this is the axis about which we have to determine the moment of inertia. So we have to consider an axis passing through the center of mass and parallel to the given axis. That is this one. Okay, this is a diameter. The moment of inertia about a diameter is mr square by 4. Okay, so mr square by 4 plus m, what is this a? That is the perpendicular distance between the two axes. Here it is capital R. So we will get 5 by 4 mr square. So 5 by 4 mr square. Okay. Now let's see the next question. The moment of inertia of a uniform circular disk about a diameter is capital I. Okay, so about a diameter is capital I means this I will be equal to mr square divided by 4, mr square by 4. Okay, its moment of inertia about an axis perpendicular to its plane and passing through a point on its rim will be. Okay. See, the moment of inertia about this point or this axis is mr square by 2. Okay, and about this axis it will be mr square by 2 plus mr square, that will be 3 by 2 mr square. Okay, so the required moment of inertia, okay, the required moment of inertia I dash will be 3 by 2 mr square, 3 by 2 mr square. Okay, and here we will get mr square is equal to 4I. Okay, so this will be 3 by 2 into 4I. Okay, 3 by 2 into 4I means we will get 6I. Okay, so the moment of inertia will be 6I. Alright. Now let's see what we have next. A flywheel rotating about a fixed axis has a kinetic energy of 360 joule and its angular speed is given. Okay, we have to find the moment of inertia. See, the expression for rotational kinetic energy is E equal to half I omega square, and I will be 2E divided by omega square. Means it is 2 into 360 divided by 30 square. Okay, this 360 and 130 can be divided. So in the numerator we will get 12 into 2, and in the denominator there will be 30. So it is 24 by 30 and it is equal to 0.8 kilogram meter square. Okay. Now next question, see, a ring of mass m and radius r rotates about an axis passing through its center and perpendicular to its plane. With the angular velocity omega, its kinetic energy will be half I omega square, and moment of inertia is mr square, so it will be half mr square omega square. Half mr square omega square means this will be the correct option. Next, a disc of radius 2 meter and mass 100 kilogram rolls on a horizontal floor. Its center of mass has a speed of 20 centimeter per second. How much work is needed to stop it? See, when it is stopped, its kinetic energy will become 0. Initially, it will have a kinetic energy of a rolling body. Means its kinetic energy will be half mv square into 1 plus k square by r square. Means total kinetic energy is translational plus rotational. Okay, that kinetic energy will be reduced to 0. Okay, so the work done will be equal to change in kinetic energy, which is equal to initial kinetic energy. So mass is given 100 kilogram, okay, and speed is given 20 centimeter per second, means it is 0.2 meter per second, and k square by r square. See, when a rolling body will have a radius, and its moment of inertia will be something into mr square. Okay, so that something is the ratio k square by r square, or k square by r square is the coefficient of mr square in the expression for moment of inertia. For ring, moment of inertia is 1 mr square, so k square by r square is 1. For disc, moment of inertia is half mr square, so k square by r square is half. For a spherical shell, moment of inertia is 2 by 3 mr square, so k square by r square is 2 by 3, like that. Okay, so here we will get this as 3 joule. Okay, work done. Now let us see what we have next. A solid cylinder of mass 2 kilogram and radius 50 centimeter rolls up an inclined plane of angle of inclination 30 degree. The center of mass of the cylinder has a speed of 4 meter per second. The distance travelled by the cylinder on the inclined surface will be. Okay. Now see, we have to find the distance along the inclined surface. Okay, and this is the deceleration when a body rolls up an inclined plane. Okay, theta here it is 30 degree, and the body here it is say solid cylinder. So k square by r square will be 1 by 2, 1 plus 1 by 2, 3 by 2. So the retardation will be g by 3. Okay, now we can apply v square equal to u square plus 2as. Here the acceleration is negative, so it will be u square minus 2as. Final velocity is 0. Okay, so s is equal to u square by 2a, and that we will get 2.4 meter. Okay, this one 2.4 meter. Okay, now see the next question. A solid sphere is rolling motion. Okay, then the ratio translational by total. Okay, translational by total will be 1 divided by 1 plus k square by r square. Here it is a solid sphere. Its moment of inertia is 2 by 5 mr square. So k square by r square is 2 by 5. 1 plus 2 by 5, that is 7 by 5, and its reciprocal will be 5 by 7. Okay, so 5:7, this one. Now next 3 objects, solid sphere, circular disc and circular ring. Okay, the amounts of work required to bring them to rest would satisfy. They all spin with the same angular speed. Okay, so the work done will be proportional to its initial kinetic energy. So initial kinetic energy will be half m k square omega square. Okay, and solid sphere, so this solid sphere, so this energy will be proportional to k square, or the ratio k square by r square. For solid sphere it is 2 by 5 and it is equal to 0.4. For disc it is 0.5 and it is 1 by 2, and for ring it is 1. So the work done will be greatest for ring, then for disc, and finally for and least for solid sphere. Okay, A is the solid sphere, that will be the least. Okay, and B is the thin circular disc that will come in between, and C maximum will be for the ring. Okay, so WC greater than WB greater than WA. Okay, okay, this one. Okay. Now see a disk and a sphere, okay, of same radius but different masses rolled on inclined planes of the same altitude and length. Which one of the objects gets the bottom of the plane first? Okay, when the acceleration is maximum, the time required to roll down will be minimum. Okay, and the acceleration is given by g sin theta divided by 1 plus k square by r square. So if k square by r square is minimum, acceleration is more, okay, or acceleration, if k square by r square is more, acceleration will be less, okay, and time will be more. When k square by r square is smaller, acceleration will be more and time will be smaller. So the body with the smaller k square by r square will have smaller time. Okay, so the sphere will reach the bottom first, that is with the smaller k square by r square. Okay, next, the ratio of the acceleration for a solid sphere rolling down an incline of theta without slipping and slipping down the incline without rolling. Okay, now rolling without slipping, this is the acceleration g sin theta divided by 1 plus k square by r square, and slipping without rolling, that is g sin theta. Okay, so we can write a1 equal to a2 divided by 1 plus k square by r square. So a1 by a2 will be, or here k square by r square, the body is a solid sphere. So k square by r square will be 2 by 5, 1 plus 2 by 5, that is 7 by 5. Or it will come as 5 a2 by 7. So a1 by a2 will be 5 by 7. Okay, so it is 5:7. Now let's see the next question. A small object of uniform density rolls up a curved surface with an initial velocity v. It reaches up to a maximum height of 3v square by 4g with respect to the initial position the object is a. Okay, now see half mv square into 1 plus k square by r square, this is the initial kinetic energy when a body rolls, and when it reaches the maximum height, its whole kinetic energy will be converted as gravitational potential energy, and h equal to v square by 2g into 1 plus k square by r square, and it is given as see 3v square by 4g, or we can write 3v square by 2g into 3 by 2. So 1 plus k square by r square equal to 3 by 2, and k square by r square will be 1 by 2. Means the moment of inertia is half mr square. So the body will be either a disc or a solid cylinder. Okay, so here we have a disc, right? Now a drum of radius capital R and mass m rolls down without slipping along an inclined plane of angle theta. The frictional force, okay, frictional force, see when a body is in pure rolling motion and when it rolls down, frictional force transforms the translational kinetic energy to rotational kinetic energy. Okay, right, work done by the frictional force in rolling motion, pure rolling will be 0 because the point of contact will be momentarily at rest. Okay, now let's see the next. A solid cylinder of mass m and radius r rolls down an inclined plane of height h without slipping. The speed of its center of mass when it reaches the bottom, half mv square into 1 plus k square by r square is the kinetic energy at the bottom, that is equal to mgh, gravitational potential energy at the top, and v equal to root of 2gh divided by 1 plus k square by r square, and k square by r square, here it will be the body is a solid cylinder, so it will be 1 by 2, 1 plus 1 by 2, that is 3 by 2, and 2 will go to the numerator, so it will be 4gh by 3 under root, 4gh by 3 under root. Okay, now let's see what we have next. A solid cylinder, hollow cylinder, both of the same mass and external diameter are released from the same height at the same time on an inclined plane, both roll down without slipping. Which one will reach the bottom first? Okay, the body with the greater acceleration will be reaching the bottom first. See, this is the expression for acceleration g sin theta divided by 1 plus k square by r square. When k square by r square is smaller, acceleration will be more and time will be less. Okay, here we have got two bodies, solid cylinder, k square by r square is 1 by 2, and hollow cylinder, k square by r square is 1. So k square by r square is smaller for solid cylinder. So acceleration will be more for solid cylinder. So time will be less and solid cylinder reaches the bottom first. Solid cylinder will reach the bottom first. Okay, now a spherical hollow ball rolls on a table without slipping. Then the fraction of its total energy associated with rotation. Okay, rotational energy divided by total energy means it is k square by k square plus r square, and it is equal to 1 divided by 1 plus r square by k square. See, in the expression for moment of inertia, the coefficient of mr square, that is the ratio k square by r square. Okay, here we have spherical ball, hollow ball. Okay, so moment of inertia is 2 by 3 mr square and k square by r square is 2 by 3. K square by r square is 2 by 3. Okay, so r square by k square will be 3 by 2. 1 plus 3 by 2 will be 1 plus 3 by 2 will be 5 by 2 and its reciprocal will be 2 by 5. Okay, 2 by 5 means the first one. Okay, next question, let us see. A thin uniform circular ring is rolling down an inclined plane of inclination 30 degree without slipping. Its linear acceleration along the inclined plane. See, we have the formula for the acceleration of a body rolling down an inclined plane, that is g sin theta divided by 1 plus k square by r square. Here the body is a circular ring. Okay, so the k square by r square will be 1 and theta here it is 30 degrees, so the acceleration will be g by 4. So g by 4. Okay, now let's see the next question. A solid sphere, disc and a solid cylinder, all of the same mass and made of the same material, are allowed to roll down on the inclined plane. Then which one will reach the bottom first? See, this is the expression for acceleration. We have disc, solid sphere and solid cylinder. See, disc and solid cylinder are having the same moment of inertia, so their ratio k square by r square will be the same. And see, when k square by r square is smaller, acceleration will be more and time will be smaller. That body will reach the bottom first. Okay, for solid sphere, k square by r square is 2 by 5 and it is equal to 0.4, and for disc or solid cylinder it is 0.5. So k square by r square is smaller for solid sphere, so its acceleration will be more and time will be smaller. So solid sphere reaches the bottom first. So solid sphere reaches the bottom first. Okay, now let us see what we have next. The speed of a homogeneous solid sphere after rolling down an inclined plane of vertical height h from rest without sliding. Okay, rolling down. See, at the highest point, the body possesses gravitational potential energy mgh. When it reaches the bottom, the whole gravitational potential energy will be converted as kinetic energy, and kinetic energy will be the translational plus rotational, and we can write half mv square into 1 plus k square by r square is the total kinetic energy at the bottom, that is equal to potential energy at the top. And the speed at the bottom, that is equal to under root 2gh divided by 1 plus k square by r square. And this k square by r square is a wonderful ratio. See, we have to use that k square by r square see at many places. Okay, so here the body is a homogeneous solid sphere and its moment of inertia is 2 by 5 mr square. So k square by r square will be 2 by 5. So 1 plus 2 by 5, that will be 7 by 5, and see that 5 will go to the numerator, so it will be under root 10 gh by 7. Okay, 10 gh by 7. This will be the answer. Okay, next is if a solid sphere is rolling, the ratio of translational energy to total kinetic energy means translational divided by translational plus rotational. Okay, so r square divided by r square plus k square, or we can write 1 divided by 1 plus k square by r square. Again we have that ratio k square by r square. See, here the body is a solid sphere, its moment of inertia is 2 by 5 mr square, so the ratio k square by r square will be 2 by 5. Okay, so in the denominator 1 plus 2 by 5, that is 7 by 5, and its reciprocal will be 5 by 7. Okay, So it must be 5:7. Children, we have discussed all the questions that appeared in NEET, past papers of NEET from this chapter, System of Particles and Rotational Motion, and before that for AIPMT. Okay, see, you have to expect only this type of questions or the questions at this level. So if you can watch this video carefully, you will be able to solve any question from this chapter, okay, that come for NEET. Okay, thank you for watching.